AP Chemistry Unit 8 is all about acids and bases and how they react with each other. It has a reputation for being one of the tougher units in the course, and it requires good math skills and a strong understanding of equilibrium. Hi there, my name is Jeremy Krug, and this is the place for all things AP Chemistry. And you're about to learn the 10 things you've got to know from Unit 8. If you're new here, welcome to my channel. Take a look around, check out my AP Chemistry playlists, that's where the action is, and make sure you subscribe. YouTube tells me that about 80% of you haven't subscribed yet, so click that subscribe button and smash that like button if you learned something from this video. And if you're serious about getting that 5 on the AP exam, check out my ultimate review packet for AP Chemistry. It's got the full review videos for every unit, complete study guides, practice questions, my exclusive tips and tricks for each unit, and 2 full practice exams in the AP Exam Simulator. You can get a free sample today over at ultimatereviewpacket.com. Now, here are the 10 things you've got to know from Unit 8. Number 1. 4 equations describe the relationship between pH, pOH, hydronium ion concentration, and hydroxide ion concentration. The first equation is that at 25 degrees Celsius, the concentration of hydronium times hydroxide ions equals 1.0 times 10 to the negative 14th. If you know one of the two values, you can calculate the other one. We also know that pH equals negative logarithm of the hydronium ion concentration. Similarly, pOH equals negative log of the hydroxide ion concentration. And finally, pH plus pOH equals 14 at 25 degrees Celsius. Let's say we have a solution with a hydronium concentration of 0.045 molar at 25 degrees Celsius. Determine the hydroxide concentration, pH, and pOH of this solution. We can start by taking the negative log of the hydronium concentration to determine the pH. That's equal to 1.35. If we know the pH, we can use this equation to calculate the pOH. We just take 14 minus pH. And 14 minus 1.35 gives us a pOH of 12.65. To determine the hydroxide concentration, we have a couple of options. Here, I'll use this equation, plug in the value for hydronium, and divide. And we find that the hydroxide concentration is 2.2 times 10 to the negative 13th moles per liter. Number 2. In acid-base chemistry, the letter P represents the negative base 10 logarithm of a value. For example, pH is the negative log of the H+, or hydronium, concentration. pKa is the negative log of the Ka value of an acid. So, if the H+ concentration of a solution is 0.0028 molar, the hydronium concentration is also 0.0028 molar. Those two values are interchangeable. The pH equals the negative log of 0.0028, which equals 2.55. Once again, that letter P just means negative log. If the equilibrium constant Ka is 8 times 10 to the negative 6th, well, pKa is just the negative log of that value, which equals 5.10. To calculate the pKb of a base, we do the same thing. pKb equals the negative log of Kb. In this example, the Kb, or negative log of Kb, is 3.55. Number 3. Strong acids and strong bases ionize completely in aqueous solution. So the pH of a strong acid equals the negative log of that acid's molarity. The pOH of a strong base equals the negative log of its molarity. In the case of group 2 hydroxides, negative log of 2 times its molarity. Strong acids are 100% dissociated. So for a solution of 0.15 molar nitric acid, the hydronium ion concentration is equal to 0.15. So to find the pH, we just take the negative log of 0.15, which is 0.82. For a strong base like 0.05 molar potassium hydroxide, the compound is 100% dissociated, so the hydroxide concentration is 0.05 molar. To find the pOH, we just take negative log of the hydroxide concentration, which is equal to 1.30. If we want to find the pH, we have to take 14 minus that pOH, which equals 12.70. Number 4. Weak acids and bases only partially dissociate, so the equilibrium constants Ka for acids and Kb for bases are used to describe their strength and to calculate their pH and percent ionization. Let's say we're asked to determine the pH and percent ionization of 0.080 molar acetic acid, where the Ka equals 1.8 times 10 to the negative fifth. Remember, acetic acid, like all acids, are proton donors, which means that water accepts an H+ ion. So we produce hydronium and acetate ions. We can set up an icebox, since this is basically an equilibrium problem. The initial concentration of the acid is 0.08 molar. The initial concentration of the products are 0. If the acetic acid concentration goes down by X, the products will increase by X. Our equilibrium concentrations are 0.08 minus X, X, and X. Now, we can write the equilibrium constant expression for this reaction and plug these values into that equation. Ka is 1.8 times 10 to the negative fifth. The hydronium and acetate concentrations are both X, and in the denominator we have 0.08 minus X. Since the value for K is a very small number, we can ignore this minus X term right here to make our math a little easier. We cross multiply and find that X squared equals 1.44 times 10 to the negative sixth. We take the square root to find that X equals 0.0012. That value for X is the concentration of hydronium. To find the pH, we just take the negative log of that value. So the pH is equal to 2.92. We're also asked to determine the percent ionization. We calculate that by taking our X value, dividing it by the initial acid concentration, and then multiplying by 100. So we take 0.0012, divide by 0.080, and find that the percent ionization is about 1.5%. Number 5. The Ka of a weak acid and the Kb of its conjugate base, when multiplied by each other, are always equal to Kw, equal to 1.0 times 10 to the negative 14th at 25 degrees Celsius, which describes the autoionization of water. So if the Ka of acetic acid is 1.8 times 10 to the negative fifth, and we're asked what is the Kb of the acetate ion, we need to use the equation Ka times Kb equals Kw. The problem tells us what Ka is, and we're solving for Kb. The value of Kw at 25 degrees Celsius is 1 times 10 to the negative 14th. We can divide and find that the Kb equals 5.6 times 10 to the negative 10th. Kw involves the fact that water undergoes autoionization. This is where two molecules of water react with each other to produce hydronium and hydroxide ions. The equilibrium constant is a very small value, 1 times 10 to the negative 14th, which we call Kw. Remember, this value for Kw only applies at 25 degrees Celsius. Most of your problems involving acids and bases will be at 25 degrees Celsius. To write that equilibrium constant expression for Kw, we omit water because pure liquids are never included in equilibrium constant expressions. So at 25 degrees Celsius, the hydronium concentration times the hydroxide concentration always equals 1.0 times 10 to the negative 14th. Some of these acid-base problems are pretty tough, and honestly, it just takes lots of practice to get better at these. I've just uploaded 60 AP-style multiple-choice questions that cover Unit 8 into the Ultimate Exam Slayer. That's twice as many as you'll find on AP Classroom. I've put the link in the description down below. Number 6. In an acid-base titration, the equivalence point occurs when the moles of acid equal the moles of base reacted with each other. In a titration, an appropriate acid-base indicator should be used to indicate visually when the pH has reached that point. So if we have an acid-base titration where 15 milliliters of acetic acid are pipetted into an Erlenmeyer flask and then titrated with 0.1183 molar sodium hydroxide solution, and if it requires 22.35 milliliters of the sodium hydroxide solution to reach the equivalence point, what is the concentration of the acetic acid solution? Well, we can use the equation molarity of acid times the volume of acid equals molarity of base times volume of base. We just plug and chug. The molarity of the acid is what we're solving for. The volume of the acid is given to us as 15 milliliters of acetic acid. The molarity of the base is 0.1183 molar, and the volume of the base is 22.35 milliliters of sodium hydroxide. We use algebra to find that the molarity of the acid is 0.1763 molar. Remember that we need to use an appropriate acid-base indicator for the titration. Since sodium hydroxide is a strong base and acetic acid is a weak acid, at their equivalence point, they produce a weakly basic solution, probably around pH 8 or 9. So we should choose an indicator that changes color somewhere around pH 8 or 9. Notice that of these three indicators, phenolphthalein is the one with a pKa, or color transition pH, that's closest to 8 or 9. So that's the one we should use. Number 7. Titration curves are produced when pH is plotted against the volume of titrant added. Titration curves can be analyzed to determine the type of titration, the volume required to reach the equivalence point, and the Ka of the weak acid used. This titration curve has an inflection point right around here that we call the equivalence point. This is the point in a titration where the moles of acid equal moles of base. And we can see that it's somewhere just above 7, maybe a little below 8. Since the equivalence point is greater than 7, we can deduce that this is the titration of a strong base and a weak acid. If the equivalence point had been less than 7, then it would have been a strong acid and a weak base. And if the equivalence point is equal to 7, that's the titration of a strong acid and strong base. How about this question? In the acid-base titration represented by this titration curve, a 15 milliliter sample of a weak acid is titrated with 0.08 molar sodium hydroxide. Based on the data given here, what is the molarity of the acid? Well, we can use the same titration equation as we did earlier. We're solving for the molarity of the acid. The volume of the acid is given to us as 15 milliliters. The molarity of the base is 0.08 molar. To determine the volume of base added, we need to refer to the titration curve. Since the inflection point is right at 25 milliliters, that's the volume of the base. So we do the math and find that the molarity of the acid is 0.133 molar. Another important point we can deduce from a titration curve is the pKa of a weak acid. And for this, we look at the half equivalence point. At the half equivalence point, the pH of the solution equals the pKa of the weak acid. Since it took 25 milliliters to get to the equivalence point, halfway would be 12.5 milliliters. And at that point, the pH is very close to 3.1. So the pKa of the weak acid is 3.1. If we had to calculate the Ka of this weak acid, we would just take 10 to the negative 3.1 power and find that the Ka of the acid is very close to 7.9 times 10 to the negative 4th power. Number 8. There are only a few strong acids. Every other acid is a weak acid. The stronger the acid, the weaker its conjugate base. Oxyacids with more oxygen atoms and or more electronegative elements tend to be stronger than acids with fewer oxygen atoms or less electronegative elements. For AP chemistry, you only have to know 6 strong acids, and here are their formulas. Like all acids, these strong acids react with water to produce hydronium ions and their conjugate bases. And since these are strong acids, their conjugate bases are very weak. In fact, they're so weak that they're really bases in name only. On the other hand, weak acids, like these 2 examples, react with water in a reversible reaction to produce hydronium and their conjugate base. Remember, the stronger the acid, the weaker the conjugate base. And the weaker the acid, the stronger its conjugate base. If we're ever asked to rank the strength of acids, we can count the number of oxygens in the formula. Here we have 3 acids that contain hydrogen, chlorine, and oxygen. But the one that has the most oxygen atoms is the strongest, because those highly electronegative oxygens cause the conjugate base to be more stable relative to the acid. So HClO4 is the strongest, HClO2 is weaker, and HClO is the weakest of these 3. What if we're given these 2 acids? Notice that acid 2 has a highly electronegative fluorine atom, while acid 1 just has another hydrogen, which is not nearly as electronegative. Since fluorine is very electronegative, acid 2 is much stronger than acid 1. Oxyacids with very electronegative atoms are stronger than other acids. Which hydrogen atom will ionize or dissociate off of each of these acids? Well, it's always the terminal hydrogen that's attached to an oxygen. So these hydrogen atoms will dissociate in these oxyacids. Number 9. A buffer is a mixture of a weak acid and its conjugate base. The Henderson-Hasselbalch equation is used to calculate the pH of a buffer given its pKa, concentration of acid, and concentration of its conjugate base. Since a buffer is a combination of a weak acid and its conjugate base, HNO2 and NO2 negative would be a buffer. HCl and Cl negative would not be a buffer because HCl is not a weak acid. It's a strong acid. It's not a buffer. This is also not a buffer because it's a mixture of 2 acids. We use the Henderson-Hasselbalch equation to calculate the pH of a buffer, which includes the pH, pKa, the concentration of conjugate base, and the concentration of weak acid. Let's say we have this problem, where a chemist needs to produce a buffer with a pH of 9.00. HBRO has a Ka of 2 times 10 to the negative 9th. If the buffer is produced so that the HBRO solution has a concentration of 0.50 molar, what should the concentration of BRO negative ions be in the buffer? The problem says the pH will be 9.00. The Ka is 2 times 10 to the negative 9th, so the pKa, the negative log of that, is 8.70. The concentration of the conjugate base, or A negative, is our unknown. The concentration of the acid is 0.50. We can subtract 8.70 from both sides and then take the antilog of both sides. We have 2.00 equals A negative over 0.50. We can cross multiply to find that the A negative concentration is 1.00 molar. So for example, we could use a solution of NaBRO or KBRO or any other solution that would produce that 1 molar solution of BRO negative ions. Number 10. When strong acids react with strong bases, the H plus and OH minus ions produce water. When strong bases react with weak acids, the acid reacts with hydroxide to form water and the conjugate base. Strong acids can react with weak bases to form water and the conjugate acid. Let's say we have a reaction where solutions of HCl and NaOH are mixed. Hydrochloric acid is a strong acid, so it dissociates completely into its ions. Sodium hydroxide also dissociates into its ions. As these compounds try to swap partners, we know that H plus and OH minus will produce water, leaving sodium and chloride as spectator ions. So the net ionic equation for this and any strong acid, strong base reaction will be H plus OH minus yields water. If we have solutions of HNO2 and sodium hydroxide being mixed, we know the nitrous acid is a weak acid, so it's not written in an ionized form, and it reacts with the hydroxide ions. Sodium is the spectator ion. Remember, in all acid-base reactions, the acid donates an H plus ion to the base. So the products will be water and NO2 negative. If we have HBr and N2H4 being mixed, we have a strong acid and a weak base reaction. The strong acid is composed of hydronium ions, and bromide is the spectator ion. Hydronium reacts with N2H4, the weak base. Once again, the acid always donates an H plus ion to the base. So the products are N2H5 plus and water. And that's it. Those are the 10 most important things you've got to know from Unit 8. If you're serious about upping your game for the AP exam, my Ultimate Exam Slayer for AP Chem has 60 AP-style multiple-choice questions for Unit 8 and for each of the 9 units. That's way more than AP Classroom. You can get my Exam Slayer along with the Ultimate Review Packet, and you'll have everything you need to succeed in AP Chem. Go check it out over at ultimatereviewpacket.com. Hey, thanks for watching. Thanks even more for subscribing, and I'll see you soon.